Welcome to the SEG Latin America Regional Advisory Committee's webinar. Our webinar series is Recent Advances and the Road Ahead. Today's speaker will be Dr. Rodrigo Portugal, and he's going to speak on conformal normal move-out correction, revisiting the basic concepts. So, Dr. Rodrigo Portugal has been working in the exploration and production industry for about 17 years. He began his career as Professor of Geophysics at State University of Campinas, and in 2009, he started working as a researcher in the E&P segment in the service companies. He currently serves as a Principal Geophysicist at Halliburton, and in 2002, he obtained a doctorate in applied mathematics from UNICAMP with emphasis on computational seismic imaging. During his career, he has published several papers and abstracts in conferences and journals. Currently, his interests are in new technologies for exploration and reservoir geophysics, and also how to apply digital transformation to such practices. The webinar today will be on conformal normal move-out correction, revisiting the basic concepts. Before we begin, if you have a question, please raise your hand in the webinar interface, and I will move you where you can ask your questions directly. If you would prefer just to type in your questions, you have two options. The question and answer box at the bottom of your screen is a great place to post your questions. And if you prefer also to, you can put them in the chat box as well. So without further ado, please welcome Dr. Rodrigo Portugal for his webinar.
Thank you, Laurie. Thank you, everybody, for attending the webinar. And thank you for SEG for the invitation. Okay, today webinar is very simple. Not complicated at all. I'm just trying to show you some revisiting of the basic concepts of normal move-out correction that I kind of stumble when I used to give lectures to students and also for colleagues here in my company, the basic concepts of processing. So let's go ahead. Well, everybody knows this formula, right? This is the normal move-out basic formula. Is this formula models a hyperbola with the parameters t0 and v. And v is the stacking velocity, maybe the stacking velocity or any velocity that you want. The thing is, and the h is the half offset. So this formula has many uses, and then you can derive this formula using the Pythagorean theorem using triangles. It's very simple, actually. And using this formula, people during these 50 years or 60 years have devised lots of process, stacking process, normal move-out correction, and everything which is based on it. So when I start to show this formula to the students and also for colleagues for them to understand what's happening during the processing, I come up with this idea that I could vary or change some parameters to see what happened with theoretical hyperbolae, compare with the data we are trying to capture. So if we keep t0 constant and changes the v parameter, we obtain this kind of cartoon here in the bottom. We have this fixed point of departure of the hyperbola, and then depending on the V, we have the different hyperbolas, or and then we can see this in these colors. The bigger the V, more flat are the hyperbola are, right? So in this cartoon, the blue hyperbola has a smaller V than the green one. And this is one thing that we can do with this formula to understand what's happening. So the idea is to trying to find the best parameters for velocity modeling or velocity analysis, or for stacking, we need to find the best T0 and V to match this seismic event. So, sorry, when we keep the V constant and change the T0, we have a different scenario. We have several hyperbolae with different colors, as you can see here. And all of them starting in different positions, but are kind of converging to the same asymptote, which is this dashed line. So again, here, we are trying to find the best pair of parameters, T0 and V, and this can be seen as a process of velocity analysis. And then when I start to look at this cartoon, many years ago, I kind of start to be a little bit intrigued by something what's happening in this figure. And then this is the starting point where I'm trying to propose here to you, and then maybe you can help me to progress with these ideas. This is ongoing research, right? So what happened is, when this is the same thing as before, I vary a lot T0 and kept the velocity constant. And then you can see here the dark line, the black lines are hyperbola of the same family. Which family is that? The family is that I change the parameter T0 but keep the V constant, and then I have many hyperbola in this set of hyperbola, and then we can say this is a family of hyperbola. And then when we zoom out this region here in this small square, we can see here lots of kind of losangles here. Actually, this is the grid that is going. Any event passing through here is going to be interpolated. So the problem is, this is what I was intrigued. When we do the NMO correction, we bring this small losangles here back to our rectangle, right? So locally, this grid is very distorted, right? But coming back to the idea that I have a family hyperbola, one thing that we can construct is a family of orthogonal hyperbola. So if it exists, it's not guaranteed that it exists, but in this case, it sure exists. So for a family of hyperbola, the black ones, we can construct another family of hyperbola, which is the blue, composed by the blue ones. And the thing which is good on it is that, sorry, they are locally orthogonal, because from the construction I impose that. So in the same region that I stressed zoom out before, you can see now that the local grid It's not formed by losangles anymore, but they are small squares or rectangles. So locally, this grid is orthogonal. And this is what I meant by conformal mapping, because when we do this, when I have this situation of, we can produce a local transformation using complex variables, which brings, can construct locally a orthogonal grid. And then just to compare, and that in region that I zoomed out before, the same region here on the left, when we use normal move-out correction, and then on the right, when we use this conformal normal move-out. Okay? Yeah, so just one more example here, comparing the nodes of the grids when we produce animal corrections. On the left, the traditional one, and then we can see here that the grid on the right, in the more or less in the middle part or in the on the right part of it, is much more well behaved because they are locally orthogonal. And then what happens if we do the correction? I have a small cartoon here. When you do on the left, with the parameterization of the traditional or familiar animal correction that we have. And then just put some figure here, this kind of a smile or semi-ellipse, just to show the effects. And on the right, the same basic image, but overlain with the orthogonal grid formed by the conformal map. Let's go ahead and see what happens with when we do the transformation. When you do the transformation, you can see the ellipse transforming in the left. I mean, on the left, we have the regular animal transformation, which stretches a lot of on the part of the image. And when we use the orthogonal, more or less, we can say that even if it's stretched, we don't have we have less blur horizontally. So it kind of preserves the geometry of the width of the event, right? And on this black stuff that we can see here on the bottom left, bottom right, and also on the left, there are not numbers, and I couldn't remove them, but it doesn't mean anything. It just it's a void, if you want. Could be zero. So the important thing is to analyze the image that we can see here, more or less on the mid-center and left. And then what happens if we use, if we do the same transformation on a seismic event? Again, I produce a synthetic seismic event. This is blur that you can see here in the images. And then when we impose the grids for the correction, we can see the grids, the distorted grids on the animal transformation here on the left, and then the thing that we are proposing here on the right, the conformal animal grid. And then when we do the correction, we have this effect. So you can see here that more or less we still have this amplifying, this diminishing of the frequency from the left to the right. This effect that we have the spreading of the wavelet. It's the same thing happens on the conformal animal transformation. But something else happened here. If you can see the blur on the left, kind of the increasing is kind of growing, it's not linear. And then on the right, it's kind of the opposite effect. So it will start the width starts at the same width on the left, but the growth of this width is kind of is not, the growth is not is kind of a linear. It's not growing more than kind of exponential for. Okay, so this is what I had to show you. This is what I'm, what I have said before. This is ongoing research we're doing now. We need to dig more for real benefits. We're expecting that we can stack more data than before. I mean, we can go further in the stacking of data, and because I think we are expecting the effect of enlarging the width of the wavelets is not that big as the traditional one. We need to test this in more realistic data and also in real data to see the effects. And also we are expecting there's something is going to happen when we try to use this to eliminate multiples and have some benefit on the stack. If you have any ideas to how to use these, please share, or any comments. Thank you very much for your attention.
All right. Thank you very much. And now we have time for some questions. All right. Well,
Nobody.
let me see. Apparently not. So if you could go back a slide.
Okay, this one?
Yes. So you've gone and you've shown how you can enhance resolution. Is there a next step for the research into making this even better?
Yes, we are going to test this using data with multiples, especially the C-bottom multiple, to see when we do the stacking, the multiple is going to be more identifiable or eliminated. We're going to see the effect of this grid on other kind of events. I mean, the noise that, like swell noise or ground roll noise, or maybe, and then also in multiple, which we can see as a noise from some parts of the processing. So our expectation is that this grid is going to enhance other kind of stuff that we are not enhancing now with using the traditional NMO correction.
Okay, thank you. We have a question, and they ask, have you tested this with coherent noise?
No, this is the next step where I was talking about. Yeah, this is a good idea to test this, maybe to enhance some or to diminish the effects of the coherent noise.
Okay. Any other questions for our presenter today? All right. Apparently not. I guess we're done for the day. Thank you, Rodrigo, for presenting for us, and thank all of you for attending. And I look forward to having you join us again in the future. So thank you very much for your attention. And Rodrigo, thank you very much as well for presenting for us.
Thank you all, and thank you, SAG, for the invitation.
All right. Thank you. Everyone have a great day. Oh, wait, we do have one more quick question.
Okay.
Well, it's not really so much a question, but a comment. We would like to see results of future testing published in SEG literature. So don't forget, when you have data that tests this, come see SEG.
Okay, sure, and we are planning to publish another kind of family of hyperbolae, and if all the mathematics behind it, and together with some better results with data.
Okay, that's wonderful. All right, everybody, have a great day. Thank you for joining us. Bye-bye.
Bye-bye.